In this lecture, we'll be continuing our treatment of chain rule. Recall, chain rule dealt with the situation where we have a dependent variable, an intermediate variable, and an independent variable. And recall, the idea is that if the independent variable changes, think instantaneous change, we have an instantaneous change in Q that's transmitted. So from T to Q via this instantaneous rate of change of Q with respect to T. So if T changes a little, it sends a change up to Q via this derivative, and then Q sends a change up to P via the derivative dP dQ, and the change happens in a multiplicative fashion. So our chain rule was that the change in the dependent variable, which with respect to T, the independent variable, was dP dQ times dQ dt. So this was one of the versions of the chain rule that we wrote the other day. Now, as an example to refresh our memories, let's remember how to do this. So we see here P is a function of Q and Q is a function of T. And we want the derivative of P with respect to T. And so using that chain rule that we just wrote, this is dP dQ times dQ dt. And we can calculate each of those derivatives from the rules we know. So P of Q is 1 over Q, so let's recall that these are easier if instead of writing 1 over Q, we write Q to the minus 1. And to get the derivative of this term with respect to Q, we use power rule, so the minus 1 comes out front, and then we decrease the exponent by 1, so we get minus Q to the minus 2. Then to get dQ dt, power rule on that expression, the derivative of t squared is 2t, and the derivative of the constant 1 is 0. This means, using our chain rule, dP dQ equals, now negative q to the minus 2, this is the same as minus 1 over q to the 2. So we have minus 1 over q squared. That's our dP dQ. dQ dt was 2t. And then remember, with these types of questions, you want to eliminate the intermediate variable from your final answer. And our q was t squared plus 1. So we can plug that in here, and this gives us our final answer. Now you may note, could we have just made the substitution from the beginning? Could we plug t squared plus 1 in for q here and compute the derivative dP dQ directly? And the answer is yes, that will work. That is a perfectly valid approach. Okay, now that we're using chain rule, we will start to look at some rates of change applications, and we will revisit this in more detail later on. But an initial example here, we have the area of a circle, and it's decreasing at this given rate. So 2 pi centimeter square per second is the rate of decrease of the area. At what rate is the radius decreasing at this one moment when the area is exactly 75 pi square centimeters? So the idea here is that you have a circle and it's shrinking. And we're told that the rate at which the area is decreasing is this constant. But the question is, as it's shrinking, when it gets to the point, the instant when it's exactly 75 pi square centimeters in area, at what rate is the radius decreasing at that moment? And the way to answer to solve a question like this is to find a way, well, first identify your variables, and then find a way to relate them. And note one variable here is area. We usually would say A, and radius would be R. And how do the area and the radius of a circle relate? Well, we know that we have the area of a circle is pi r squared. And this would be in centimeters squared in our application. Now let's think about, in this question, what other information are we given, and how can we translate that information into things dealing with these variables or the way they're changing. And notice the first thing we're told is that the area of the circle is decreasing at a rate given here. So the rate at which the area is decreasing in time, that should make us think dA dt. So there's our instantaneous rate of change of the area of the circle in time. And we were just told there that this is constant. How about the other sentence? We're asked at what rate is the radius decreasing at this particular moment. So what we're asked for there is the rate of change of the radius, so dr dt. And then we have this one instant, which we haven't addressed yet, but we will momentarily. So we have some variables. We have a relationship between these variables. And then we have some information about the derivatives in time of these variables. So the first thing we'll do here, now that we have this set up, is note that what we want is dA dt. And we're thinking of area has an intermediate variable of radius and then an independent variable of time. And so we want to think in terms of chain rule. We have a change in the area of the circle due to r, and then a change in r due to time. And our chain rule tells us that dA dt, so this overall change here, is equal to dA dr times dr dt. Well, dA dr, we can calculate this. Because A is pi r squared, we can take the derivative of A with respect to r. dA dr equals, pi is just a constant, and then r squared we do power rule, 2r to the 1. What else do we know? Well, we know that dA dt is constant. dA dt here is equal to that constant. So we're using that dA dt of being a constant 2 pi centimeters squared per second here. Putting this all together gives us that 2 pi. Actually, we should be careful. It's decreasing. So we should note that we have a negative sign because we're decreasing. The area is decreasing. So we have a negative 2 pi that's our dA dt, equals dA dr, we just saw was 2 pi r from this calculation times dr dt. And we can now solve for dr dt. So note that the 2's cancel, the pi's cancel. Solving for dr dt, we only have to divide both sides by r. And so we have dr dt is minus 1 over r. So at any given time, to get the instantaneous rate of change of the radius of the circle, we find the radius of the circle at that time and plug it into this expression. Now, we are asked to find this at a specific instant. In particular, we're asked to find it when the area is 75 pi square centimeters. So using this dr dt, we can plug in this case when area equals 75 pi. Well, we need r when this happens, but of course, if the area is 75 pi square centimeters, we know the area is pi r squared. So we can solve for r, and we'll get r is equal to the square root of 75. So this value, dr dt at the instant when the area of the circle is 75 pi, also corresponds to the instant when the radius is root 75. Plugging that in to this expression for dr dt, we have minus 1 over root 75, or if you prefer, root 75, negative root 75 over 75, which is approximately 0.1155 centimeters per second. So this is a classic type of example where you're using chain rule, where you have a dependent variable, an intermediate variable, and an independent variable. And it's very common for these types of questions to use chain rule when you have some relationship between variables and then you want to start changing things in time. We generally call those related rates questions, and we will get into those in much more detail a little bit later on. But this is a standard application of chain rule. An issue we now address, having chain rule in our toolkit, is the issue of vertical tangent lines. And we will see that chain rule will be instrumental in actually determining if a function has a vertical tangent line. The idea of a vertical tangent line is that at the point a, f of a, if f is continuous there, and the absolute value of its derivative is approaching infinity as x approaches a, we have a vertical tangent line. Now we can see this with a picture. So let's suppose this is x equals a, and let's draw a vertical dashed line here to make things easier. Now, first of all, note that the point a, f of a exists, and f is continuous there. So what we have is some point here on the function, a, f of a, and we know that if we approach the function from the right, the limit of the function has to be this f of a value, and the same is true if we approach from the left, because the overall limit exists because of continuity. at a. However, the absolute value of the derivative is approaching infinity as x approaches a. So let's think about, in this case, let's say as we come to a from the right, let's say that the derivative is getting infinitely large. Well, what is the derivative? The derivative is the slope of the tangent line. So as we approach a from the right, as we get closer and closer, the tangent line is getting steeper and steeper until when we get all the way, the tangent line becomes vertical. So in this picture, you can imagine as you're getting closer and closer to x equals a, you're getting steeper and steeper tangent lines. This is what it means for the tangent line to actually straighten up exactly at x equals a. Its derivative, as x approaches a, its derivative is approaching infinity. And we could also say in this case, let's say this is also the limit as, well, why don't we do it a little different? Why don't we say the limit as x approaches a minus of f prime of x. Let's say it was minus infinity. Well, in this case, notice that this is still satisfied, because if we took absolute values, if we did the limit, so this tells us that the limit as x goes to a minus of, again, the absolute value of f prime of x would be positive infinity, because the absolute value would turn it, the expression, positive. But if it's, as we approach x equals a from the left, if the derivative is approaching negative infinity, we're getting steeper and steeper tangent lines with negative slopes. So we'd be coming in something like this. So as you get closer and closer to x equals a from the left, your tangent line is getting steeper and steeper, but with a negative slope. And in this case, by the way, this is what we call a cusp. And this is actually a situation where the function, like in the corner point that we looked in the earlier lecture, there's no derivative at x equals a. In this case, this is also a scenario where there is no derivative. The derivative does not exist at x equals a. But this is the idea for vertical tangent lines. So let's do a couple examples and see how this works. So the first example would be the cube root of x. And this is something we're used to because we know what this graph looks like already. We know this graph is actually just the graph, think of it as just the graph of y equals x cubed flipped on its side. And we can see that at 0, at x equals 0, we have this vertical tangent line. Well, how do we show that? First, let's rewrite this as x to the 1/3, so it's easier to calculate its derivative. dy dx, our power rule says bring the 1/3 out front, and then reduce 1/3 by 1. 1/3 minus 1 is 1/3 minus 3/3, or negative 2/3. When you do derivative calculations, it's always easier to have x to your exponent. When you start interpreting things, it's easier to get rid of negative exponents by moving things back into the denominator. And remember what the issue is here. Let's go back. We have a vertical tangent line at a point if the absolute value of the derivative is approaching infinity as x approaches a. In this case, we'd be going to 0. So let's think about what's happening with the limit as x goes to 0. of this dy dx. So we have the limit as x approaches 0 of 1 over 3x to the 2/3. And the way we can think of this, it'll be easier to see, this is the limit as x goes to 0 of 1/3 times, why don't we say 1 over x squared raised to the 3rd. So we have the cube root of x squared in the denominator. So first of all, as x goes to 0, and the reason we write it like this is because sometimes with these questions you have to look at the limit from the right and the limit from the left. Because as in the previous example, you can have f prime of x approaching, say, positive infinity when you come from the right, and then f prime of x approaching negative infinity as you come by the left. But because this definition says take the absolute value of the derivative, you still get a vertical tangent line. So you have to set yourself up to think about this derivative if you take an absolute value sign coming from each side. In this case, what's nice is because x squared is positive, so this x squared term is going to be positive. That means the cube root of that x squared is also positive. So we know that this expression is positive, regardless of whether you come from the right or whether you come from the left. And that makes sense in the picture. Think about getting close to x from the right here. You have a very steep tangent line with a positive slope, but the same thing as if you're coming to 0 from the left. You're also very steep with a positive slope. So what we have here, as x approaches 0, x squared is very tiny. The cube root of that tiny number is also tiny. So as x goes to 0, this denominator is getting smaller and smaller, approaching 0. But something tiny in the denominator results in something gigantic. So this is approaching positive. This limit is infinity. So the limit, of course, remember, it means it doesn't exist, but this is a type of non-existent limit where we're saying that it's unbounded, getting unboundedly large. So we say it's infinity. And this confirms that this has a vertical tangent line. At x equals 0. Okay, let's look at another example. Given this function, let's find all points where the tangent line and I think, let's see, yeah, find where the tangent line is vertical or horizontal. Now the first thing we want to note is we have to be careful about the x that we use. We know that we can't be taking a square root of a negative number. So we require that 4 minus x squared be greater than or equal to 0, or x squared less than or equal to 4, which means if x squared is less than or equal to 4, then we need x to be between minus 2 and 2. So our domain is the interval minus 2, 2. And so we can concentrate on this domain and figure out where does this function have horizontal or vertical tangent lines. The first thing we will need will be the derivative. So we know g prime of x, we get bit complicated because we will need product rule and then chain rule. So product rule says first, and remember, maybe we rewrite g of x as x times the quantity 4 minus x squared to the 1/2. So for product rule, we say first, which is x, times the derivative of the second, and we use our chain rule. So the derivative of the outer function, bring the 1/2 out front, leave the inner part alone, reduce the exponent by 1. So we have 1/2 times the quantity 4 minus x squared to the negative 1/2 times the derivative of the inside. Derivative of 4 is 0. Derivative of negative x squared minus 2x. So this is the first term for our product rule. Then we have this plus the second. Times the derivative of the first. The first is just x, so its derivative is 1. And we clean this up a little bit. So we can see this 2 and this 2, well, the 1/2 and the 2 cancel. And the x terms will combine to be x squared. And we have a negative that's out front. So in the numerator, we'll have negative x squared. And note that 4 minus x squared to the minus 1/2, that's the same thing as 1 over 4 minus x squared to the 1/2, or having a root 4 minus x squared in the denominator. For this second term, we just have root 4 minus x squared. So to answer our question, we have two pieces. One, we want to answer the question where the tangent line is horizontal. And if you think about a function having a horizontal tangent line, and we will get into this in much greater detail, but horizontal tangent line means that your slope will be 0. So these are points where your tangent line is horizontal, and you see there are points where the slope of the tangent line is 0. So for horizontal tangent lines, we set the derivative g prime of x equal to 0 and solve. So g prime of x equals 0 is the same thing. Take this expression and set it to 0. So setting this equal to 0 gives us root 4 minus x squared equals x squared over root 4 minus x squared. Multiply both sides by root 4 minus x squared. The left-hand side will become can write it out, root 4 minus x squared times root 4 minus x squared equals x squared. This, of course, this product is 4 minus x squared. Adding x squared to both sides gives us 4 equals 2x squared, or x squared equals 2. This means both x equals root 2 and x equals minus root 2 give us points, or x values, at which the tangent line is going to be horizontal. Let's find the y values so we can take a shot at plotting this. G of root 2, go back to the original function, plug that in. for x, we get root 2 minus root 4 minus root 2 squared. So again, we're just taking root 2, plugging it into the original function. Sorry, this isn't minus, this is times. So this is root 2 times, we have 4 minus root 2 squared, so 4 minus 2, which all simplifies to root 2 or 2. So this gives us the point root 2, 2. We plugged in root 2, and we saw the y value was 2. Similarly, g of minus root 2, plug in minus root 2 here. The only difference will be that this term, when we plug in minus root 2 here, it's going to introduce a minus sign. So we're going to get minus root 2 times the quantity 4 minus root 2 squared, but this negative 1 will square to a 1, and we'll get a very similar answer, except we have a minus sign. So we have a negative 2. So this gives us the point minus root 2 minus 2. So these are the points at which we have horizontal tangent lines. For vertical tangent lines, we need to check for this infinite behavior, this infinite limiting behavior of the derivative. So let's take a look on the next page. And so let's draw things so that we can keep track of what's going on. So we know the domain of the function is the interval minus 2, 2. And then we just saw that we had horizontal tangent lines at the points root 2, 2 and minus root 2, minus 2. So root 2 is about right around 1.4. So maybe here is our root 2, and over here is our minus root 2. So we have the point root 2, 2, and negative root 2, negative 2. And we know the tangent lines are horizontal at those points. We can also get a little bit of an idea. Notice if we plug in x equals 0, we get 0. So we know g of 0 is 0. So we also know that the graph goes through the origin. And let's rewrite things on this page. So we had g prime of x was equal to this expression here. So let's just rewrite that so we have it. We have g prime of x equals root 4 minus x squared minus x squared over root 4 minus x squared. And so vertical tangent lines, remember the key thing. The key thing is some kind of weird limiting problem with the derivative. And when you look at this derivative, we've already determined that the domain of the function, and thus the derivative as well, is the interval -2 to 2. And then we have to ask, where are the trouble spots that we can run into this derivative not existing? And it looks like what we need to be careful of is division by 0. So we see that we get division by 0 if 4 minus x squared equals 0. Well, that's x squared equals 4, or x is 2, or x equals -2. So we should expect, we still have to actually look at it, but we should expect these vertical tangent lines of x equals 2 and x equals -2. So let's think about this derivative. Let's think about first the limit. And we have to be a little bit careful with our limits here. We have to stay within the domain of the function. So if we handle x equals 2 first, we see that we have to come from the right, because it doesn't make sense to look at an overall limit. Sorry, we have to come from the left. It doesn't make sense to look at an overall limit or a right-sided limit. So we look at the limit as x approaches 2 from the left of g prime of x. And let's think about what that looks like. So this is the limit as x goes to 2 from the left of root 4 minus x squared minus x squared over root 4 minus x squared. Now think about using your limit laws, which we often interpret as directly evaluating the limit. This term here, this first term, is approaching 0. This x squared term is approaching 2 squared, which is 4, so this term is going away. There's no trouble there. The problem here, so it doesn't matter whether, well, the sign of 2 being squared. So this numerator is staying positive. In fact, it's approaching 2 squared. It's approaching 4. But the denominator is approaching 0. It's staying positive, but it's approaching 0. So it's getting smaller and smaller. So this term, this whole term, right this way, is approaching infinity. But don't forget there's a minus sign here. So this limit is -infinity. This satisfies our requirement for a vertical tangent line. What it means is, as we approach 2 from the left, the tangent lines are getting steeper and steeper, but they have very large negative slopes. So we can now take a guess at what this should look like, at least over on this side, is that we're going to have this here, we have that horizontal tangent line, but then we get this vertical tangent line as we approach 2 from the left. Similarly, we can look at the limit as x goes to -2, but now we have to look from the right. So we're honing in on x equals -2 from the right, staying in the domain of the function, of g prime of x. And it's going to be the same kind of reasoning. Limit as x goes to -2 from the right of root 4 minus x squared minus x squared over root 4 minus x squared. And the same reasoning will give us the same conclusion. The fact that 2 is negative, we're approaching -2, and the negative value, when we square this, we're squaring x everywhere. So the negative value isn't changing things from how it behaved when x approached -2. So we have the same conclusion of -infinity. And so as we get closer and closer to x equals -2 from the left, we're getting steeper and steeper tangent lines with large negative slopes. And so we have essentially the reflection of through the origin of this picture on the other side, where you have that horizontal tangent line there, and then we hone in on this vertical tangent line when x equals -2. So this is the idea, and generally the approach we took right here is the right one. You calculate your derivative and then say, where are the trouble spots for that derivative? Do we get any infinite limiting behavior of the derivative at any particular x? And that's how you fish for your vertical tangent lines. So to be complete, to answer the question, we would say that in this case, g of x has vertical tangent lines at the points (2, 0) and -2, 0. And by the way, I may have jumped there to conclude this, that we had these zeros for the y values, but you could see that when we went back to the original function. G of 2 is 2 times √4 - 4, or 0. So we could see that g of 2 was 0 and g of -2 was 0. So we obtained those points that way. So our vertical tangent lines happened at these endpoints here, according to our definition, if we're thinking of them in this one-sided limit sense, restricting to the domain. Some calculus books may tell you that you don't have a tangent line here because the overall limit doesn't make sense because you have no left-sided limit at -2 or right-sided limit at +2. But that's okay. We can still talk about this type of infinite slope happening at x equals -2 or +2. Another example, this goes back to the illustration we gave when we introduced the idea of vertical tangent lines, is this y equals the square root of absolute value of x. And this may be a little bit intimidating to look at initially, but first, let's just draw it. Think about the two cases. If x is positive, this is just y equals √x, and we know y equals √x looks like this. But then if x is negative, then you're taking the square root of, instead of -x, the absolute value of x makes it a positive x. So it will just be, to the left of the origin, just the reflection of this graph about the y-axis. And this is the example, as we mentioned in the introduction of the idea of a vertical tangent line, where we have a cusp. So you could think about this, you think of a cusp like, it's not like a corner. If you bump into a corner, maybe you get a bruise. If you bump into a cusp, you get stabbed, because you can think of it as this has an infinitely fine point. So this is like the tip of a sword with an infinitely fine point, which is different than a corner. But how do we see this? Well, let's break it into the two cases. If x is greater than 0, then this is just y equals square root of x, or x to the 1/2. And so dy dx is 1/2 x to the minus 1/2, or 1/2 root x. And let's think about what's happening as we approach x from the right. So this means the limit as x approaches 0 from the right of dy dx is the limit as x approaches 0 from the right of 1/2 root x. And think about this. This is a denominator that's staying positive, but getting really tiny. So you have 1 over something really tiny. This gives you this unbounded, this infinite style limit. And that's a reflection that as you're honing in on 0 from the right, these tangent lines are getting steeper and steeper with very, very large positive slopes. We then look at the approach coming from the left, and in this case, note that since we have y equals the square root of minus x, as specified here, our dy dx will be different. So that's, of course, negative x to the 1/2. So dy dx will be 1/2 times minus x to the negative 1/2 times the derivative of the inside function, which is minus 1, or minus 1 over 2 root minus x. So when we look at the limit, and again, we're coming from the left now. So the limit as x goes to 0 from the left of dy dx, we have the limit as x goes to 0 from the left of the expression that we just calculated. And we can make the same type of conclusion. This x is going to 0. The x is coming to 0 from the left, so it's negative. So we have a minus minus, so there's no problem under the square root sign. But you have something in the denominator, you have the numerator fixed and something in the denominator very, very tiny. So the whole expression is blowing up, it's exploding in size, but the minus 1 out front now is making this be negative infinity. And that reflects that as we hone in on 0 from x equals 0 from the left, the tangent lines are getting steeper and steeper, but the slopes are now negative. And so this shows us explicitly how we do have this vertical tangent line and a cusp here at x equals 0.